Hello and welcome for my presentation of the process development method for high-speed gluing and about a reproduction case study. My name is A.Müller. After a short introduction about myself, I'll give you some background information about high-speed gluing and the production of lithium-ion batteries, and then we're going step by step through the design method for high-speed gluing, and I will show you with my case study how to use this design method exactly. I'm working for the Institute for Machine Tools and Factory Management IWF at the Technical University of Berlin, especially for the chair of handling and assembly technology Hamster. I'm working on soft robotic simulations for handling and assembly, especially in heavy-duty soft robotic grippers. And parallel to it, I'm working with my colleagues on a project for high throughput production technologies for lithium-ion batteries. So if you're interested in our work, just take a screenshot or grab your phone and scan these QR codes, and then you can follow us on LinkedIn, YouTube, or go directly on our homepage. So let's start with the motivation. In branches with high throughput like microelectronics and battery production, you want to avoid time-consuming handling tasks like pick-and-place operations. So you see a picture with 3 different colors, and each color represents 3 different products which have to stack above each other in a specific sequence. So if you want to reduce this sequence, so the cycle time, you have to accelerate, you have to increase the acceleration or the velocity to get smaller cycle time. But you have still the problems with the standstill times. You cannot avoid them. So in this kind of productions, we are looking for much more continuous process to avoid these time-consuming handling tasks. So if you're in an environment with high velocities and accelerations, there is no problematic when you just handle one product. But when you add another product on it, you have to look for a specific velocity curve, and you can avoid it when you improve the pre-product stability. In this case, you can glue to add these products together, and then you are able to drive with full speed again through all process. So gluing is one solution to counteract this problematic. But now I will show you the necessity of high-speed gluing. When you have an electric vehicle, you found a battery package inside of it. Inside of this package you found single battery cells, and when you open it, there exists a stack out of electrodes and separator sheets. In our case, it's a Z-folded electrode or separator compound. Usually you're using pick-and-place operations, which we want to avoid. So my colleagues and myself are developed a continuous Z-folding process, and for this process we need a motion, a joining process where we join the separators in motion, and this is why we need a really fast joining process. So normally if you want to join electrodes and separators, you use a hot lamination process with a material speed of maximum of 400 mm per second, but there exists some problematics. You have to use heat, and the heat produces a long curing time, and if you drive too fast through this process, the sheets can begin to curve and you have to orientate it afterwards, and you cannot use every separator. So sometimes you have to pre-coat the separator that you can even join it in the lamination process. So we are looking for a coat assembly process which doesn't use the heat, so we have a much more smaller footprint, and we are looking for a process with a material speed of 1 meter per second to increase our throughput. But actually there exists no design method for high-speed gluing, so we developed one, and here we are. Let's start with our design method for high-speed gluing. So you're starting with the requirement analysis. It depends on your application case, what kind of requirements you have to look at it, and then you compare these requirements with the given processes for your use case. So you compare everything with each other and take the best suitable process steps, and then you have to analyze this process because you have no knowledge about this process step for your use case. So you can use a Chicago diagram, FMA analysis, SWOT analysis. It depends on your application case. And then we have a process validation. And in this process validation, you start with easy test, like a manual test. in level 1, so you have to put little effort in it, but you build really fast your first knowledge about it, and then depends on application case how much effort you have to put in. So you're going to level 2 and can end in level 4. But what does it exactly mean? I will present in our use case. So let's going through our design method for high-speed gluing with our. So in our process, we are looking for a joining process of lithium-ion batteries, and we are handling with really sensitive materials. So we want to looking for damage-free handling processes. So as an example, we want to avoid tactile processes, and we have to looking for a variable cycle times because the cell format can change. It depends on the automotive restrictions, what shapes or sizes they are looking for. And in our case, we are looking for really fast curing time under 1 second to reduce this footprint. So this is just a selections of our requirements. When we have a list of our requirements, and then we're going through the possible gluing bonding processes. So there's just some examples out of the VDE 3821, for example, spray application, floor nozzle application, and so on. But when you're going deeper inside the research, you found much more methods for these processes. So we compared all these different methods with our requirements and see that our jet dispensing system is the best suitable method for us. So at this stage, we know we want to use our jet dispensing system, but we have knowledge about our parameters which have an influence in it. So we're starting with the Ishikawa diagram and going through all correlation parameters which have an influence on our adhesive strains for our bonding process. So there exist in the beginning a lot of question marks, and then we're starting with our process validation in the level 1, which means we are just using a manual test bench. So we also using a tactile dispensing, which we want to avoid lately, but we just use it to build our knowledge for the first parameter setups. So we're going backwards to the process analysis, and then we know a lot about the adhesive. In this case, you can test different joining parameters, so we can check which separators and which electrodes are working with each other with these adhesives. What is with the mixing ratio of the adhesive, so it depends on the viscosity and the homogeneity, how long we can storage our glue, and so on. So you get a lot of information in just with a little effort. But the human has the biggest impact on the repetitive accuracy about other test strains. So we were going to the level 2 semi-automated test bench, where we replaced our human interactions with automatizated access. Then we could put the human out of the equation, and we add some measurement methods so we can direct measure our curing time, our shear stress, and we can also vary the parameter for our machine. So we can change our parameter settings, so we can control the curing time, the line pressure, but we have still question mark on the adhesive quantity. So this is why we have to go through the third level, where we replaced our tactile dispensing with automated dispensing. And here you see the video sequence. On the left side you see the dispenser. He's applicate a point of adhesive on the electrode, and then we're rolling over with our separator on the electrode and pull out and measure the shear stress with our beam loads. So this is our level 3 test bench, and you see we have to put more and more effort in it, but our results are reaching a much more high accuracy. So at this level we know which parameters have the biggest impact on the adhesive strains, and we're doing afterwards in DOA with this parameter setups. We see that the close time, as an example, has the biggest influence, and so you can design your parameter, your machine with this results. And so we don't have to go for level 4 because our accuracy level is high, but we have to build some coin sets because we have to check the chemical performance of the cells. So we glued some cells and built some coin sets with it and compared it with a non-glued one. Then we charge and discharge them of 100 times and compared the discharge capacity. You see a difference about 11%. But what does it exactly mean? So if you build a coin cell, you use a diameter of 60 millimeters, you add, in our case, 5 microliters spot of glue, roll over, and you produce a 65 square millimeter wetted area. This means we have a wetted area of 32%. And this is a discharge capacity degrees of 11%. But when you scale up to an automotive industry battery format, then you have a wetted area of less than 1%, and this means you have a discharge capacity in a linear direction of 0.23%, which is nearly nothing. So I will present you a new method for high-speed glue application. It depends really on your application case, how much effort you have to put in to get your results. And we checked and we proved it that it will work with our really specific topic. So actually we are building our joining machine, and if you're interested in our project work, you can join us about our homepage. So thank you for your attention. And these are my colleagues and myself. Really appreciate it to work with them. Thank you.